Okay, can you see my slides? All right. So today we're gonna move to the next process. Quite a long part of lithography process in the last few sessions. So now we're gonna look at etching process. So as usual, before we continue the next topic, so let's recap a few things from the previous topic. All right. Okay, let's go to the question number 1. What are the requirements of a good photoresist? What are the properties, requirements or properties, typical characteristics of a good photoresist? If you have to say 3, then what would be the 3? High resolution, yep, good, of course, high resolution, number 1. How about the second one? High sensitivity, yes, very good. High sensitivity to light. High etch resistance, yep, that's good. So it needs to resist where it isn't supposed to be etched. And we're gonna see how etching looks like today. And ada lagi? So now I've got 3. Explain this now, so not to list down to be able to by solution edge resistance and good contrast, maybe right contrast the gradient that the gradient is coming for. We don't want it to be too low. We want to be high because you wanna see the step change between your Q0 and QF. Good alignment is not for the resist, but rather is for the scanning process, right, Naim? Ada lagi ya? Right, so let's move on to the low defect density. Yep, yes, low defect density, good, right? You don't want to have defects from your resist testing as well. So explain lithography process. Good addition, yes, good addition. So you want the resist to adhere to the HMDS and the wave, and you don't want to have pattern collapse and the process. So those are, at least you've got 5 already. So make sure you know how to explain each of the right. Explain lithography issues related to CD of a printed feature discussed yesterday. So explain lithography process issues related to critical dimension of a printed feature. So let's explain 2 process issues related to CD. So what are they? On? Anyone? Hazika, what is one of the process issues related to CD?
Develop defects.
Sorry?
Develop defects.
Develop defects. So defects due to development process or due to the process?
Due to during the develop yang dia jadi tak stable tu, yang dia jadi over or underdeveloped.
Okay, so it's either underdeveloped or overdeveloped, right?
Yes.
All right, good. Right. So one of them is underdeveloped or overdeveloped. Well, if there's a question on this, you can actually have 2 points for both. So one is underdeveloped, one is overdeveloped. So those are actually two issues, but on the opposite side of each other. So one is over edge, or sorry, one is overdeveloped, one is underdeveloped. Right. Anything else? Any other issues related to CD? Liana? Liana? Anything else? Issues related. Suryati? Can I mute off, or you can also chat box? First, CD? I just want to ask it. Down on uh those is problem with the question that issues related to the future uh, to CD. Ada lagi isu lain? You can also finish. You can say green box cannot be an issue, or the what else? Top for me also be a C related problem. Uh, is then to difference in being measured, because it's from the topics. Just imagine you features on wafer have teeth of a man. You actually see from is him yang sedang no, and you from you're looking at them being there or the or highest at the top this actually, so it's actually a form of the function can also be LER with right on stay It's a huge problem in lithography. Explain ways. So how do we solve standing? So can you relate CD? So how standing wave? Jenny, how solve standing wave? Come on. How do you solve standing wave? Two ways that we've discussed. Back, right? Bottom anti-reflection coating, bottom anti-reflective coating to minimize the reflection from the silicon resist interface, and then you will reduce the formation of standing wave. Yep, optimize the PEB process, right? Those are the two ways to solve the standing wave problem. You should be able to explain as well how does each of your answers now can solve the standing wave, right? Right, PEB, same. Right, finally, what are the main requirements in the next generation lithography system, or you can phrase as advanced lithography system? What are you looking for in the advanced lithography system? The final part of yesterday? You know, you have a look at it, okay? So next, let's move on to the next process, which is etching. Lithography cannot survive without etching. So, and on the other hand, if you cannot etch if you don't have printed features. So etching cannot survive without lithography either. So they actually work hand in hand with each other, right? So anyone with experience on etching in your FYP? On etching last time, except my students. Shamim and Liana work on inverted pyramids by etching. Ada etching dalam you punya FYP sebelum ni? Etching of anything. Have you ever etched anything during your experience in School of Physics? Pernah etch apa-apa? Have you ever etched anything? Nope. Right. Okay, that's fine. So what is etching? Etching is actually removal of material. So bahasa yang paling mudah adalah removal of material, right? So if you look at this particular figure, so this is actually the surface of photoresist, but when you did your lithography, the photoresist yang was originally flat throughout the surface, and then after the lithography you have your features printed just like this, all right? So just like this. So when you want to do etching, you want to etch the resist, and eventually you want to have your features on silicon. So remember, kita punya integrated circuit ni is formed on the silicon, right? It's not on the resist. Resist ni is only an intermediate stage. It's only a medium for you to get your features on the silicon. And the silicon is the active material for the device. So walaupun kita dah print kita punya feature on the resist will not be there forever. The resist will be removed eventually. But whatever you have on the resist, you want the same pattern to be transferred to silicon. And that's why etching is needed, right? We're going to see how, and we're going to see why. So what is etching? Etching is the process of removing solid films. Etching process can be divided into wet and dry etching. So just like the way we divide thermal oxidation, wet and dry, so you can also divide etching process to wet and dry etching process, right? If you talk about wet etching, so it associates with the usage of wet chemicals like acids or alkaline solutions in order to do the removal process. If you talk about dry etching, it is associated with the usage of plasma or ionized gas in a vacuum chamber in order for you to do the removal of the solid films. So wet uses wet chemicals and dry etching uses plasma in order to do the job. So what characterizes etching? So either it's wet or dry. So the first one is isotropicity. Isotropicity here means etching nature in a non-directional process, right? So that means kalau you etch in isotropic environment, so the etching or dry, you're going to etch the material in all directions with equal etch rates. Nanti kita akan go through etch rates, tapi saya just cover kat sini dulu. Equal etch rates in all directions. So equal etch rates in all directions. Maksudnya dia akan remove the material top, right, bottom, left, and any direction in between with equal etch rate. So you're gonna typically end up with equal removal of material in all directions in comparison to the etching location, right? On the other hand, if you talk about anisotropic means unidirectional. So maksudnya dia akan etching yang guna tu either it's in a wet etch environment or dry etch environment. It's gonna etch your material, resist ke, whatever lah, silicon ke, oxide ke, nitride ke. So it's gonna etch your material in unidirectional nature. Ataupun dia ada specific direction yang dia akan etch more than other directions. So in that case, the etch rate is not equal in all directions, but it's higher in one direction, but lower in other directions. So we call that as an isotropic etch, right? So isotropic equals in all direction, and isotropic not equals in all direction. The second characteristic of the etching is called selectivity. So this one relates to the relative rates at which two chemically distinct solid film are etched by an etchant. So if you have, for example, silicon dioxide on silicon, so you put them in an etchant solution, so they're gonna be etched differently because the selectivity is different, right? Some chemicals are designed to etch oxide, some chemicals are designed to etch metals, some chemicals are designed to etch silicon, and so on and so forth, right? So they have their own selectivity. All right, introduction to etching, removal of unwanted material from the wafer surface. You want to remove some parts of the material from the surface. So etching generally can be divided into three. The first one is pattern etching. So you want to remove some parts of your patterns from the surface. So you can also say this one as the removal of the resist from the patterns, because you have got your patterns after the lithography process. So you want to remove the resist further, but before that you want to do something else as well before the resist is completely removed. The second one is called unpatterned etching, where removal of a layer is done blanket. Well, this one you can also consider photoresist is the resist is blanket. That means if the resist has no patterns yet, you can also remove the whole resist completely. It can be done as well. But on the other hand, you can also remove resist in the pattern etch where the resist already formed the pattern. So it can be both, depending on how to use the etching. The next one in the unpatterned etching is also for ox ataupun sacrificial oxide ataupun oxide yang you grow in order to be eventually sacrificed. So you want to etch the oxide blanket, or you want to etch the nitride as well blanket. So this one is called unpatterned because there is no patterns to deal with. It's just a blanket layer of something that you need to remove eventually. Then wafer cleaning is also one of the examples of etching process, because in order to clean your surface, you have to etch some parts of the surface, right? According to the materials that you want to remove, especially when you talk about contaminants or residues from previous processes. So if you look at if you relate this to the previous process, which is lithography after the CAD process, you have seen that, okay, for example, if you look at the first one there, if you want to, for example, you deposit a layer of something, for example, by a CVD process. We're going to cover this one later on how do we do the thin film deposition process. For example, if you have material A deposited on the resist, all right, well, you can also say this one as oxide, maybe. Kalau you dah grow oxide, silicon oxide on top, you've grown the whole surfaces of silicon, but you remove oxide dekat tepi dengan kat belakang, so you're now left with the top oxide. Then you spin the resist, you send the wafer to CAD process, you spin the resist, and then you expose the areas and unexpose some other areas, just like what we learned in the lithography process. And then you develop the patterns, so you are now ready for your etching process. So after your CAD, you're going to be left with this feature, okay, up to what we have learned before. So you have got your mask, you've got your features, resist features on the wafer, and then under the resist, you've got your blanket SiO2, for example, and then done. So next, so you've done your lithography here. Okay, katalah ni you buat oxidation. So this one is all lithography, and this one lithography. And now you're going to do your etching here, So now it goes into. So what's going to happen is you can send the wafer and then etch the exposed area. So you can eventually etch this area. Selectively dalam etching, so that's what you actually get here. So you etch the exposed side, for example, selectively. It's very unidirectional, so maksudnya dia target just vertical etching lah, that you can etch the exposed area. Kalau you go for isotropic etching, for example, dia akan makan semua oxide in all directions with equal etch rate. So you will probably end up with rounded feature kat bawah ni, sebab dia kena makan juga. Dia akan makan kat sini sikit, because the etch rate is similar in all directions. But in this case, we want to use a unidirectional etching. Then you remove the etching, and then eventually, after you've got your oxide patterns, then your next step is to actually remove the resist mask. You remove this one, you etch this one, then you're going to be left with pattern oxide, for example. Okay, so remember last time, I think I did ask you about how do you pattern your oxide, and we're going to learn in our next topic or so. So this is how you can pattern your oxide or your other layers, right? So you need to have your resist on first in order to define the areas to be removed and areas that and then the open areas will be etched in the etch process, and then the resist will eventually be removed because it's just an intermediate stage for you to do the etching process. In this case, for example, you're going to be left with patterned oxide. For example. You can also do pattern nitride or pattern some other layers. So in this case, kalau you nak pattern oxide, this is how it looks like, because you cannot do the patterning on oxide directly, just like one of the questions last time, because it's not a photosensitive material to begin with. So you still need some help from the photoresist to define the areas to be able to eventually pattern the oxides for your processing, right? So from my explanation just now, you can see a few things are highlighted. It's about selectivity of the etching and directionality of the etching, right? So that's how it looks like for you to etch your oxide, for example. So there are some terminologies that you have to be familiar with when you talk about etching process. The first one is etch rate, just like what I've explained just now. So etch rate is basically the removal rate of the material in a specific direction or in all directions. So depending if you're talking about isotropicity or anisotropicity of the etching process. The second one is selectivity. The third one is anisotropy. So in this case, it refers to whether your etching is isotropic in nature or anisotropic in nature, whether it's wet or dry etching. So the fourth one is uniformity or homogeneity of the etch on the surface. So let's go through one by one. Etch rate is the speed at which etching occurs. So that means how much material, well, the material can be silicon, resist, oxide, nitride, metals, being removed in certain period of time. So typical unit is nanometer per minute. Well, if the removal is so much, for example, if you're talking about microns removal per minute, then your etch rate can also be in micron per minute. It can also be nanometer per second. If it's too slow, you can only remove like a couple of nanometers per single second. So it can be acceptable as well. So as long as your etch rate is reasonable according to the removal of material. So it can be in nanometer, it can be in micron, it can be over minute, it can be over hour, it can be over second as well. Selectivity is the ratio of etch. So for example, SiO2 etching with hydrofluoric acid, when you want to remove your silicon dioxide, you can do that by HF etch or HF dip. So it's about selectivity of the etchant towards SiO2 and silicon. If the SiO2 is on the silicon, then so the etchant has to selectively etch the material that is supposed to etch and not etching the material that is not supposed to etch, right? So determine the etch time for a 1-2 micron thick SiO2 films. The typical one is somewhere 400 nanometer per minute, right? So then you can actually do some calculation if you have a resist on or something, depending on the selectivity of the etchant. Etch rate and selectivity are crucial for defining mask, whether it's photo or hard mask. So just like what we discussed in the couple of slides before. So when you want to use your resist as your mask and you want to etch the underlying layer and then actually remove the mask, so the etching selectivity will be very, very important. Hold on, you cannot move to the next page. All right then. Okay, let's look at anisotropy. Anisotropy ataupun anisotropicity sama aja. Ataupun isotropicity pun actually sama aja. So anisotropicity and isotropicity is just the opposite of each other. So kalau you isotropicity, then you are talking about it's more isotropic. If you're talking about anisotropicity, then usually it's more anisotropic. Okay, so isotropic etching remove material equally actions, it undercuts the mask. So if you look at the figure on the left, so you have your mask on, for example, assuming your mask is the resist that you've got from your CED process, photoresist. So assuming after your CED, your underlying layer under the mask is not yet etched, and then you have silicon. Sekarang kalau you letak dalam isotropic etchant yang akan etch equally in all directions with equal etch rate. So this is how it's going to look like after the etching process. So katalah you letak dalam chemical yang isotropic in nature. So dia akan katalah chemical tu punya molecule kat sini. So what it does is it will etch the material with equal etch rates in all directions. So dia akan makan semua sama je. But unfortunately, the mask dia tak boleh makan lah sebab dia tak selectivity is different, right? So it's supposed to two down here. Then so that's what it's. So if you put into isotropic, that's how the feature is going to look like after the etching process. On the other hand, if you use anisotropic etching, anisotropic means yang satu direction. Well, usually this one is done in plasma. Maksudnya you hantar plasma to do the bombardment, argon ion usually. Argon plus ataupun argon ion lah, if like. You need to ionize argon gas to be argon ions, and then you direct the plasma to etch the surface in one direction, so dia akan makan vertically. So as a result, dinding ni will not be affected. Dinding will not be affected. So it will just stay vertical as designed ataupun as printed in the litho process, right? So that's how it looks like anisotropy. So anisotropic etching removes material only perpendicular to the surface, accurate transfer of mass pattern. So if talking about the accurate transfer of the mass, the resist that you have printed after the CD process, then you need to use anisotropic etching for the process. Anisotropy is defined as vertical etch rate minus horizontal etch rate over vertical etch rate. So how vertical is that in ratio? So it's given by 1, well, you can simplify that as vertical over vertical, and that is 1, and minus horizontal over vertical. So 1 minus horizontal versus vertical material removed, and then you can define your anisotropicity then. So the higher the anisotropy, the more vertical structure is. Sebab kalau you 1 minus, if it's very vertical, then that means 1 minus horizontal is not much versus so much, not much divided by so much, so you're going to get something close to 0. 1 minus something close to 0 is close to 1, so that is very, very anisotropic. Uniformity and homogeneity, so it measures distribution of the etch rate across the surface. So when you're talking about 8-inch or 12-inch or 18-inch, you want the etchant to etch with equal etch rates throughout the surface. You don't want it to etch more in the center, less at the edge, and eventually you're going to end up with a non-homogeneous surface. But on the other hand, you want to make sure that everything is equal on the surface, so that the etch removal, the material being removed across the surface is just uniform, right? So it can be across the wafer in one wafer. It can be across a couple of wafers in one batch, like this wafer to that wafer, that wafer to that wafer. So it can be across batches. So, well, it can be within wafer, it can be across wafers, it can be across batches as well. Batch 1, batch 2, batch 3. Be across different equipment as well. Etching equipment 1, etching equipment 2, and 3. How uniform are they in terms of the etching capability? Right, so in summary, etch rate, if you talk about etch rate, then it's about the film thickness being etched per unit time. So it can be nanometer per minute, nanometer per hour, micron per minute, micron per hour. It can in fact be per second as well, depending on how much you remove and how much time do you need. And the significant effects on the throughput. So the higher the etch rate, is the throughput lower or throughput higher? So let's test your understanding so far. If your etch rate is higher for your process, will the throughput be higher or lower? What do you think? Throughput again is through that particular process or in time. Have higher etch rate, will your throughput be higher or lower? Anyone? Come on, guess. Farah Hazwani? Anyone? Amira? No, Amira? Come on, let's give a guess. Hi, Azika said hi. Amira said hi. Yes, it's high. Betul? Not sure? Well, it's high actually. Kalau you punya throughput of your process is high, sorry, if your hash rate is tadi. Can you hear me now? The line interruptions get. Can you hear and see me? All right, let me reshare. Nampak slide? Nampak slide? Can you see the slides? Right, good. So yes, if you can remove a lot in a short time, so your process recipe needs to be a short one. So then as a result, you can run more wafers per unit hour, so your throughput will be higher as well. Etch uniformity is about variation of etch rate throughout one wafer. It can be across wafers, it can be across batches, it can be across equipment as well. Selectivity, the ratio of etch rate between two different materials. So for example, if you want to etch silicon dioxide on silicon, so the selectivity has to be high or else you won't see accurate removal of the material you want to remove. Anisotropy is about directionality of the etching. So if you etching all directions with equal etch rates, then the process is said to be isotropic. If you're etching with higher etch rate in one direction in comparison to other directions, so the process is said to be anisotropic. If you talk about undercut, then you are talking about unilateral overetch. So for example, if you go back to this particular slide, so this green layer, this green oxide is called undercut. So dia makan kat bawah, dia makan kat bawah, dia makan dalam sikit. So that is labeled, that is called undercut. So you're not supposed to remove that, but due to the nature of the chemical or the whatever they use in the etching process, due to the isotropicity of that etchant, so you result in undercut condition. Right? So you typically don't want that undercut to happen. All right, etching characteristics. We have discussed yesterday that the CD that we printed in the CED, we call it DICD or Developed Inspection CD. And the CD that we have after the etching, after the etching is called what? Oh, what is it called again? Kalau DICD is for litho process. Kalau etching kita panggil apa? WCD lah. What's the CD that we call? The ICD versus FICD. Yes, good. FICD, yeah, Final Inspection CD. So DI versus FI. So kalau kerja dalam fab, either it's Infineon or in Soltera atau mana-mana fab, well, they usually monitor DI FI bias. So how much difference do you get after DI versus FI? So it's going to be recorded as DI FI bias. And this DI-FI bias is also documented in the process specification. So maksudnya DI-FI pun dia ada dia own SPC chart. You cannot exceed certain limits. So you don't want to be different so much after your etching process in comparison to CED process. Right. Well, the critical dimension final is actually referring to FICD. The etch bias is etch feature size minus printed feature size, or you can also say FICD minus DICD. So etch feature size minus printed feature size. So what you see there isn't always what you get. So if you're saying from the top, just like I drew just now, I think atas you akan nampak yang warna hijau tu je, tapi you don't see the width of the oxide under the resist cut due to the DIFI bias. Okay, so bila you dah etch, baru you tahu what is the exact CD of your printed oxide, right? Right, this is severe undercut. You can see the oxide is so much undercut due to the isotropic nature of the etching. All right, so isotropic etch in this case, etch in all directions. Features are enlarged, so dia akan makan semua. So you will end up with a bowl-shaped feature. So normally, if you see bowl-shaped feature, then it's due to isotropic. Okay. On the other hand, if you see something like this, then it's due to the anisotropic etch, because one direction is etched more than others. So you akan nampak straight feature salah, macam resist punya feature. So anisotropic etch is highly directional, feature sizes are preserved, and side walls are nearly vertical. So nearly vertical usually. Walaupun you punya argon ions, we're going to learn later on, the plasma etching dia akan makan sikit in the horizontal direction, but it's not as much as the etching process in the vertical direction. Sebab dia is targeted, dia macam ditembak, is bombarded in y-axis instead of x-axis. Tapi dia punya impact tu akan terasa lah dekat x-axis. So that's why we normally say that it's nearly vertical, but it's not completely vertical if you compare to the litho features. So only achievable when you talk about plasma etch, right? So vertical features are only obtained in plasma etching. But if you talk about anisotropic anisotropic etching overall, so anisotropic ni tak semestinya vertical je. It can also be if you use wafer, for example, silicon wafer, grain orientation or this orientation is 100. We're gonna see later on. Etching also means some grains are etched at higher rates in comparison to others. So some orientation is etched at higher rates in comparison to others. For example, we're gonna see later on that 100 is typically etched with higher rate in comparison to 111 or 101 if you run an anisotropic process. But that process doesn't produce vertical structures. Dia akan produce structure yang bentuk lain. But then it's still anisotropic in nature. So maksudnya kat sini anisotropic tu bukan vertical sahaja, but then it also covers some other shapes yang bukan bentuk bowl. Right? If you see bowl, then it's completely isotropic. But if you see certain shape, inclined shape ke ataupun some angle, or you can see that particular shape is so systematic, is so repeatable, then you can call it anisotropic as well. Right, let me cover maybe 2 more slides. All right, another etching characteristic is called aspect ratio. So aspect ratio is the complexity of the etch in terms of its width and depth. Well, usually when you talk about aspect ratio, the equation will be depth over width. So maksudnya if you look at the figure on the left, right, the aspect ratio is about 1 because the depth is equal to the width of the feature. So in this case, the feature is oxide. So the height of the oxide is equals to the width of the oxide. So therefore, height or depth over width is equal to 1. So 1 over 1 is 1, right? On the other hand, if you look at the middle illustration, so the height is higher than the depth. Sorry, the height is higher than the width. So in this case, it's double of the width. So 2 over 1 is 1. So your aspect ratio is 2. right? And on the other hand, on the rightmost diagram there, you can see that the height is about half of the width. So therefore, your aspect ratio is 1/2 or only half, right? So this is referring to different cases of aspect ratio of your features. So as the aspect ratio increases, the difficulty of the etch also increases. So if you compare these three aspect ratios, you rasa proses etching mana yang paling susah untuk produce aspect ratio yang 3 ni? To produce 1 or 2, 1 or 1, 2 when you talk about etching. Any guess before we close the session? Two, 1. Is it 2, 1? Any other guesses? One with 1, 1 or 1, 2? Well, generally it's 2, 1. Generally it's 2, 1. Dia macam konsep korek telaga. Kalau nak korek sikit je lagi senang kan. Nak korek lagi dalam lagi susah lah. Sepatutnya that's how it goes. But it depends on the the angle that you want to explain. Kadang-kadang if the ratio is too low, for example 1, 2, if your oxide thickness is too thin, it can also be difficult as well. Sebab your process has to be very accurate and very slow in terms of the etch rates. But just imagine if your oxide that you're working on is about 4 nanometer thickness under the gate, so you don't want your etching process to go so vigorously, right? Because after all, the oxide thickness is only like 4 nano, so you want your etching process to be in good control, super accurate, and in that case it's quite difficult as well. So in comparison to the deepest ones now, the aspect ratio of 2, 1 is equally difficult. Cumanya the challenges is not the same as what you can see on 1, 2, because it's about getting deeper and deeper, and maybe at that point your etch rate doesn't have to be so accurate or doesn't have to be so small, because you have quite some time to dig into the oxide before you remove completely. So the challenges are different on both cases. So this one example of the anisotropic etching. So in this case, it's not 4 to 1. It's actually more than 4. I think it's about 5, maybe 5. The height of the silicon is about 5 times the width, maybe. So in that case, about 4 to 5 in terms of the aspect ratio. All right, so I think I'll just stop here for today. So we've covered some introduction to the etching process. So any questions for etching? Any questions for now? Can you follow the process? All good? Any problems so far? Anyone with questions? Tak ada? Tak ada means all good, semua faham, Right then, okay, on Monday, I'm gonna bring one colleague from my, not from the past lah, saya punya kawan lah sebenarnya. So we work together in Sultan last time, and then he moved to Singapore, Avago, to work in a fab as well. So he's gonna be in on WebEx with us during the class time, 12 to 1, right? 12 to 1, Monday, for some sharing on his industrial experience. Okay? So kita tak akan continue on etching on Mondays, but then it's gonna be more of experience sharing and stuff like that. So that's one. Second one, I'm in the middle of arrangement with Osram. Dia punya R&D director dah setuju, Dr. David Lacey dah setuju to join us on WebEx, right? Where after mid-sem break on 7 and 8 of December, I think it's on Monday and Tuesday, class time. So he is going to assign 2 engineers, I think, or maybe one engineer, I'm not sure. In the first class, on the 7th, Osram is going to cover LED fabrication process for front end fabrication process. So that's what they're doing in Kulim High Tech Park now, the front end epitaxial and everything. And then on the second day, on the 8th of December, Osram is going to cover the LED fabrication process for back end, right? Back end, that's what they're doing in Bayan Lepas, Penang, right? So the R&D director has agreed on the slots. It's just that I'm waiting for the names of engineers who's gonna join us on the sessions, right? So you're gonna see how the LED is fabricated. Hopefully everything goes well. So I'm gonna make an official announcement later on, and probably some other physics student will be joining us as well. I'm gonna open the session to others as well, and perhaps to the lecture as well, so that everybody can learn on the LED fabrication process. Who knows? Osram could be your internship place, or in fact your career, for your first career, right? So if there is no question, then I'll see you on Monday for the industrial sharing by my friend, right? So bye-bye, take care, Assalamualaikum, have a great weekend.